Today we're going to start talking about inequalities in one triangle. And this is really the beginning of when we start to really look in depth at what's going on in a triangle. And of course we already know that triangles are made up of 6 parts, 3 sides and 3 angles. And that is just the beginning of the story with triangle. And so today we're going to look at what one triangle really needs in order to be a triangle. So I've broken this down into 2 critical understandings for the day. Critical understanding number 1 is that the side length varies directly. Varies directly, of course, means that if one gets larger, the other has to get larger as well. Side length varies directly as angle measure. So if a side length gets bigger, then the opposite angle measure has to also get bigger. So this means that you can order angle measures based on side lengths. The side lengths, of course, opposite the angle. And vice versa. You can order side lengths based on angle measure opposite the side. Okay, so we'll talk about what that means more as we get into some examples. Critical understanding number 2 is that side lengths must fall into a range in order to form a triangle. Otherwise, one of 2 things will happen. Either the triangle would collapse in on itself, or it would never close. And so you may be starting to think, well, this seems really complicated, but really there's a lot going on in geometric figures, and a triangle is the most basic geometric figure in planimetry, so we are going to spend a lot of time this year talking about them. And so I want you to start thinking about triangles as more of an interesting, changing thing rather than just a shape that you can draw on a piece of paper. Also, I hate the word shape, so please don't ever call it a shape. Okay, so and we'll be using compound inequalities to think about this. Compound inequalities, of course, we learned last year in algebra. We'll review those as well. Okay. So I want to just quickly look at this on Geogebra. Using the sliders, these are sliders right here. Using the sliders, explore possible lengths of the sides of a triangle. Can you figure out what has to happen so that you can actually form a triangle? So we have this one side, this side right here, side AB, which has length of 13. Side AE that has length 3, and side BF that has length 7. And right now it's obviously not a triangle. So remember the 2 things I said that would happen here. Let's go back to this. The 2 things I said would happen here are either, of course, it'll collapse in on itself or it'll never close. So out of those 2 possibilities, which one do you think is happening right here? Well, it's never closing, right? Because it's essentially just a U. There's no connection between points E and F. So what do we need in order to make this work? Well, obviously it looks like side A at the bottom there, lowercase a, it looks like it's way too long. Of course, the longer I make it, the farther apart these 2 points get, point E and point F. They're getting farther apart. So we could shrink down angle A. Okay, that might work, right? We could shrink down angle A, or side A. What if we put it right here, where side A is 10, and we leave side B as 3 and side C is 7? Well, that's not going to work, is it? Because 7 and 3, you notice here, they're not quite on top of each other. What's happening here? This side is 3, this side is 7. Adding them together, you get 10, but that's all that this side is. So if we actually leave them as 3 and 7, what's going to happen here in order for these to line up is it's just going to collapse in on itself like that. And it's not going to be a triangle anymore, it's just going to be a line, right? It's going to be 2 lines on top of each other. Then, of course, if we move out angle A again, or I keep saying angle, side A again, then it, of course, doesn't even connect anymore. Let's see what happens if we make one of these a little bit longer. So let's make this 4. So now we have side B is 4, side C is 7, and side A is still 10. 4 plus 7 is 11. So really we can work on this now, because if we were to collapse these down like this, notice that they're overlapping a little bit right here. And that little overlap, which how long is that overlap going to be if I collapse them down all the way down here, all the way down? The overlap is going to be 1, right? Because of the segment addition postulate that we've already learned. So because this is 4 and 7, which makes 11, 1 longer than this 10. But that tells us that if we can find that if we actually have an overlap, then we can put these out here somewhere so that they actually make a triangle. So that's one thing to think about, is that the 4 plus 7 has to be bigger than 10, and that's really what we're going to be getting at with this critical understanding number 2. Okay, so what happens if I drag this out to 11 now? And so now look that side A is 11. It's not going to work anymore because this is 4, this is 7, and when I drop them down, it's going to collapse back in on itself, and it's just going to be 11 and 11 on top of each other, right? So what if we move this out to 5? Well, now it's going to work again because we have 5 and 7, which is 12, and the bottom side is 11. So we can carefully find a spot where they indeed overlap, and where they meet. And I'm trying to be as careful as I can with the mouse, but you get where I'm going with this. So it forms a triangle now. Well, let's see if we move this out to 12. So now side A is 12. It's going to collapse again because 5 and 7 overlap perfectly to make 12, which is exactly what that side is. So we do have to extend this one more. And of course it doesn't have to be exactly one more, because we can have different shapes and sizes of triangles. They don't all have to look like that, right? I can, for example, I can make this come out here, and I can make not quite as acute of a triangle. I can make these both 8. I can make it isosceles. Now it looks like an isosceles triangle. So there's lots of different configurations for this. But ultimately, if you notice, any 2 lengths, let's take any 2 of these lengths right here, and I'm just going to make this different so that it's actually a scalene triangle again. So now all 3 of the sides are different lengths, right? It makes a triangle. But let's take any 2 sides and add them together. 6 plus 8 is 14. 14 is bigger than this 12. Okay, what about 8 plus 12 is 20. It's bigger than this 6. And 12 plus 6 is 18, which is bigger than this 8. So what we're seeing here is that if you take any 2 of the sides of a triangle and add them together, the sum is going to be bigger. It has to be bigger than the third remaining side. And that's a really critical understanding here. That's actually this critical understanding 2. In order for them to either not collapse in on themselves or never close, you're going to have to make sure that any 2 of the side lengths are bigger than the third one whenever you add any 2 of them. And so if we think about that, any 2 side lengths must be bigger than the third one. Let's consider here a triangle with 2 sides, 7 units and 3 units. It doesn't matter if they're centimeters or inches or miles or whatever. They're just units, right? 7 units and 3 units. And let x be the remaining side. So we essentially have, what I'm saying here is we have some, I'm just sketching this out, some, triangle. We don't know anything about it. Here's 7, here's 3, and here's x. So let's see what this looks like. Obviously this is not drawn to scale because the 3 is way too long, or the 7 is way too short, depending on which way you look at it, but it's just a sketch. So we know 2 of the sides are 3 and 7, and then the last one is x. Well, if we think that any 2 of the sides has to be bigger than the third one, the sum of any 2 sides has to be larger than the remaining side. So let's take 3 plus 7. Okay, here's this. 7 plus 3, 7 plus 3. these two added together has to be bigger than x, so that has to be bigger than x. Or these two, x and 3, has to be bigger than 7. So there's that one. And then lastly, x and 7 has to be bigger than 3. So x plus 7 has to be bigger than 3. So let's think about this, okay? Let's use our algebra skills and solve these inequalities real quickly. If 7 plus 3 has to be bigger than x, then this means that 10 is bigger than x, which means that x is less than 10, right? That's what that means right there. I'm just writing it backwards. It means 10 is greater than x, which means x has to be less than 10. Okay? If we subtract the 3 from both sides here, we have x is greater than 4. Okay? And here, if we this is already true, because if we know x is greater than 4, then this 4, or let's say this is 5 here, 5 plus 7 is greater than 3. That's already true. You see what I'm saying there? Because we know x has to be greater than 4. So let's say it's 5. 5 plus 7 is 12, is greater than 3, which is already true. So we're good on this one. So look at what we have here. We have two inequalities. We have x is less than 10 and x is greater than 4. So let's write that as a compound inequality. Let's write that as a compound inequality. So x has to be greater than 4 and x has to be less than 10. We learned how to write compound inequalities last year in algebra, and so we know that if x is the remaining side, it has to be between the lengths of 4 and 10. It has to be somewhere in that range. And we know all of that just by given 2 of the beginning side lengths. So there's lots of more interesting stuff than that meets the eye to triangles. Okay? So let's look at a couple of examples here. And I'm just going to kind of touch through some of these here just to see what you think. Okay? Alright. Order the angles in each triangle from smallest to largest. Okay, so we have these three side lengths, 14, 18, and 16. Well, 14 is the smallest out of the three, so the angle across from it also has to be the smallest. So angle J has to be the smallest. Okay? And then 16 is the next biggest, so the angle across from that has to be the next biggest, angle K. And then 18 is the largest, so the angle across from that has to be the largest, so it's angle L. Okay. Or let's see, we can do the same thing and just sketch it out here. Triangle RQP, and it does, I don't really know what this is, I'm just drawing in here. So QP is 15, RP is 25, and RQ is 13. Obviously, again, not to scale, it's just a sketch. So this is the largest. RP is the largest. RQ is the smallest. If RQ is the smallest, then angle P has to be the smallest angle. And then this is the next biggest, so angle R is next. Again, I'm looking across the triangle like that. So if I know this is somewhere in the lineup, I just go across to find the angle that corresponds to it. And then, of course, angle Q is across from the largest side, so it has to be the largest angle. Okay? Let's see. Okay. By the way, a circumstance of this is that when you have an isosceles or an equilateral triangle, that's how the angles end up being the same, because they're across from the sides that are the same, and so that's how that's related to each other. Let's look at something called the triangle inequality theorem. This is, by the way, this is critical understanding number 2. This is called the triangle inequality theorem. Not a very good acronym, but that's what it's called. Triangle inequality theorem. So state if the three numbers can be measures of the sides of a triangle. What about 7, 5, and 4? Well, are 7 plus 5 greater than 4? Yes. What about 7 plus 4 is greater than 5? Yes. What about 5 plus 4 is greater than 7? You see how I'm doing this? I'm just taking any two sides, 7 plus 5, and it has to be greater than the last one. Or 7 plus 4 has to be greater than 5. Or 5 plus 4 has to be greater than 7. If all those are true, then it can be a triangle. That's true, and that's true, so this is a yes. It can be a triangle. Let's jump down here maybe to... Let's do number 2, right here. 3, 6, and 2. 3 plus 6 is greater than 2, which is true. 3 plus 2 is greater than 6, not true, right? Not true. So because any one of the, but we can keep going here. 6 plus 2 is greater than 3. That's true, but this one fails, so the answer is no. This cannot be a triangle because one of these fails. Starting to make sense now? Okay. What about 1, 13, and 13? In case you're wondering, that would be a really skinny, tall 1, 13, and 13. Isosceles triangle, like that. Right? So 1, 13, and 13. Okay, 1 plus 13 is greater than 13. Yes. 1 plus 13 is greater than 13. Yes. And 13 plus 13 is greater than 1. Yes. So this is yes. And they all three work. What about what about I don't know. What about this one? Let's look at this one. 5, 8, and 4. 5 plus 8 is greater than 4. Yes. 5 plus 4 is greater than 8. Yes. And then 8 plus 4 is greater than 5. Yes. So that's a yes because they all three work. Okay? What about if two sides of a triangle have the following measures? Find the range of the possible measures for the third side. So again, when we did this over here, we essentially, if you notice, 4 was our lower bound and 10 was our upper bound. We were given 7 and 3. A shortcut to get there is that 7 minus 3 equals 4 and 7 plus 3 equals 10. And so there's our lower bound and our upper bound. So you take the existing sides and you just subtract them and you add them. So 9 minus 5 is 4, 9 plus 5 is 14, so there's our upper bound, and our lower bound. So we know the third side, x, has to be between 4 and 14. See what I mean? So if 11 and 8 are given two sides, then 11 plus 8 and 11 minus 8, 11 plus 8 is 19, 11 minus 8 is 3. There's our upper bound and our lower bound, so the third side has to be between 3 and 19. Make sense? Okay, that's it.